Hi guys, welcome to 11.2 Infinite Series. Last section we talked about sequences. Today we're going to build on that. We're going to talk about infinite series. Series are just the sum of the terms of the sequence. So here's an example of a sequence. Just a reminder, the notation that we used. We would say that this sequence is equal to, it looks like it's powers of 2 in the denominator. We start our sequence at 1, we go to infinity. So this would be the sequence. From this we can take it, if we add this infinite collection of numbers up, we are creating a series. So a series is just a sum of the terms of the sequence. So notation we would use for this, in math, we use the Greek letter sigma. So sigma means sum. So we're summing up all the terms, and we use a sequence notation next to the sigma. We start at 1 and we'd go on forever. Interesting note, this sum, even though we're adding an infinite collection of numerical values, so if we add this up forever, 1/32, 1/64, it actually just equals 1. So we can add an infinite sum of numbers and get a finite value. My best justification for this right now, let's look at this picture. Let's just look at a square, a 1 by 1 square. So let's suppose we have a square. So this is 1 unit by 1 unit. And then let's look at it in parts. I'm gonna break it in half first. So let's take this part right here. So that's supposed to be in half. I know it's not quite in half, so that you agree that the area of this is 1/2. So 1/2 plus, I'm going to take what's remaining, cut that in half. So this has a quarter. I'm going to add 1/4. So we're at 3/4 of the area of the square. I'm going to cut this in half. And this is going to be 1/8. 1/8. All right, I'm going to cut what's remaining in half. This would be 1/16 of the square. So if I add that in, and if I do this indefinitely, you'll see we'll never completely exhaust the square. This is 1/32 of the square, and I add that in. If we do this infinitely, 1/64. Right. And we do this indefinitely, it's going to fill up this total area of 1. I think that's so super cool that an infinite sum can take on a finite value. Not always the case though. Let's look at another infinite sum. Let's look at this series by adding the terms of the sequence 1, 1/2, 1/3, so forth and so on. So here's my sequence. This is our notation and goes from 1 to infinity. This is our harmonic sequence. The corresponding series would be 1 plus 1/2 plus 1/3 plus 1/4 plus. So this would be the corresponding series. The notation we would use. Same notation as a sequence, although we would just throw the sigma out front, indicating that we're adding all these terms up. And this actually is infinite. So just by slightly altering the terms of the sequence, still looks like we're adding tiny quantities each time, but they're not small enough. In fact, when we add these up forever, it will equal infinity. So my best justification for this is, let's compare it to the graph of 1/x. All right, so let's look at the graph of 1/x from 1 to infinity. And let's check out, let me find a light colored pen here. All right, let's look at the area from 1 to infinity. So if we go back to our chapter 7, notes, we see that the peach area under here is equal to from 1 to infinity 1 over x dx. And to find this area, we would take the limit as t goes to infinity, integrate from 1 to t, 1 over x dx, which would be the limit as t goes to infinity. The antiderivative of 1 over x dx is just the natural log of x. I don't need the absolute values because we're integrating from 1 to infinity, which is all positive. The limit as t goes to infinity of the natural log of t minus the natural log of 1. Which is equal to the limit as t goes to infinity of the natural log of t, because the natural log of 1 is 0, and this limit is infinite. So this area is infinite. There's infinite area under the curve to the right of 1 under the function f of x equals 1 over x. All right, so how does that prove that this series is actually infinite? Well, we're going to make a comparison here. I'm going to draw some rectangles. Let's consider this rectangle right here. Has a height of 1 and a base of 1. So this rectangle has area 1. I'm going to look at this right here. Has a height of 1/2 and a base of 1, so area 1/2. 1/3, so forth and so on. So let's consider this green area now. So do you agree the green area is greater than the peach area? Let's do this for a minute. Let's do this, yep. So the green area is equal to 1 plus 1/2 plus 1/3 plus 1/4 forever, which is equal to the sum of 1 over n, then goes to 1 to infinity. But we can see that all these rectangles fall above the peach area, so this is greater than the peach area, which is 1 to infinity 1 over x dx, which is infinite. So actually this sum is a larger infinity than the peach area. So therefore, this sum has to also be infinite. All right. All right, let's move on to the formality of this stuff. Given a series, which is the sum of the terms of a sequence, so the series from 1 to infinity of an is a1 plus a2 plus a3. We're going to look at what we call the partial sums. And depending on how the partial sums behaves determines how the overall series behaves. So the partial sum is just the sum of the first n terms. So given the series from 1 to infinity, the first partial sum is just the first term of the sequence. The second partial sum is the sum of the first 2 terms. The third partial sum is the sum of the first 3 terms forever. And what happens is that this now becomes a sequence itself. I don't know if you can hear my cats making horrible sounds, but please ignore their misbehaving. Is now itself a sequence. So how this sequence behaves determines the convergence of the series. I know this looks a lot more horrible than what it is. We're going to come up with some nice techniques to have to avoid doing this, but it is all part of the deal. All right, so if the sequence of partial sums converges, then the original series is called convergent, and we write that the series converges to the limit of the partial sums. If the limit of the partial sums diverges, then the original series also diverges. So for example, this is, if n is 1, we're at 1/2 plus 1/4 plus 1/8 plus 1/16 forever. So the first partial sum would be just the first term. The second partial sum would be the first term plus the second term. And if we do that math, we get 3/4. The third partial sum is 1/2 plus 1/4 plus 1/8. And if we add those together, we get 7/8. We continue on forever and see how these ending numbers behave. And in this case, we're going to get 15/16. And what we do is we start to try to look for a pattern in these numbers. These numbers produce a sequence of partial sums. So the first partial sum is 1/2, the second is 3/4, the third is 7/8, the fourth is 15/16. If I do the fifth, I'm going to get 31/32. If I do the sixth, I'm going to get 63/64. You can confirm all that. And I see a pattern here. In general, the nth partial sum is going to be, well, this was 2 to the 4th, that's 2 to the 5th, that's 2 to the 6th. So it's 2 to the nth power. And then this is 1 less than 2 to the nth power. So if I wanted to know what the 100th partial sum is, it would be 2 to the 100th power minus 1 over 2 to the 100th power. So we want to know how this guy behaves. And how this guy behaves is going to determine how the original series behaves. So here we're looking at the sequence of partial sums. So the limit of the sequence of partial sums for this particular example is, well, now we have to go back to our calculus days, 2n minus 1 over 2 to the n. Now, before we start getting all fancy, I'm just going to do some algebra here. As n goes to infinity, I can split a fraction up by distributing the denominator to each of the terms in the numerator. So 2 over n is, I'll write it out, minus 1 over 2 to the n. So this limit is just the limit as n goes to infinity of 1 over 2 to the n. So this term here, this goes to 0. So this limit is just 1. So therefore, the sum of 1 over 2 to the n equals 1 to infinity is equal to the limit of the partial sums, which is 1, where each partial sum can be found by this template. So we showed this 2 different ways. I showed this drawing the box and looking at each of the little pieces in the box by continually to divide it in half and adding up the areas of the smaller pieces. And then we also looked at it as a set of partial sums. All right, let's look at another example. Again, don't get too freaked out about this. We are going to come up with methods other than examining partial sums. All right, let's look at this series. So this series corresponds to the sequence -1 to the n. So if I look at this, if n is 1, my first term is -1. If n is 2, -1 squared is +1. So this is just the alternating forever. Okay, so my first partial sum would just be the first term, -1. My second partial sum would be the sum of the first and the second term. My third partial sum would be the sum of the first, the second, and the third. So those cancel out. We're back at -1. My fourth partial sum would be -1 plus 1 plus -1 plus 1. We're back at 0. And we're going to continue like this. And we're looking at how these numbers behave. We can see logically that they're just going to alternate between -1 and 0. So the limit as n goes to infinity of this series does not exist. It's not infinite. It's not a value. It's just going to continually bounce back and forth between -1 and 0. So therefore, we can conclude that this series diverges. If it doesn't have a sum, if this limit does not exist, then the corresponding series diverges. Okay. Continuing right along, let's bring ourselves back to our geometric sequences. A geometric sequence is a sequence obtained by starting with a number and obtaining the next number by multiplying by the constant each time. So here, 2, 4, 8, 16. I know to get from 2 to 4, I multiply by 2. 4 times 2 is 8. 8 times 2 is 16. So my constant ratio is 2. Right? And this would be the sequence 2 to the n. Right? So A would be 1, because that would be, right? Nope, sorry, A would be 2. Nope, A would be 1. We'd have to start with 1, because it'd be 1 times 2 to the n. So here, 1, 1/3, 1/9, 1/27. Right, so my ratio, to get from 1 to 1/3, I'd multiply by 1/3. To get from 1/3 to 1/9, I'd multiply by 1/3. Right? So this is, now I have to be careful here, because it's not 1/3 to the n. If I left it like this, and I go from 1 to infinity, so here's where it gets a little bit tricky algebraically. If I start with 1, 1/3 to the n would give me the first term of 1. So I need a coefficient out front here to force my first term to be 1. So I can see that if I put n equals 1, I get 1/3. To bring it back up to 1, I need the constant 3 out front. So 3 times 1/3 to the n power from 1 to infinity. So my constant here would be 3. So be careful here. A is 3. You have to make sure, and this is an easy check by just plugging in, starting with 1, plugging it into your template for your sequence and making sure that it produces the given sequence. All right, so today we're going to talk about a geometric series, which is just the sum of a geometric sequence. So the series from 1 to infinity, 2 to the n, is going to be 2 plus 4 plus 8 plus 16 forever. This one would be, well, if n is 1, we're at the 1. 1/3 to the 1 is 1 times 3 is 1. Plus, and then 2 would be 1/9 times 3 would give me the 1/3 plus 1/9 plus forever. So my first partial sum would be 1. My second partial sum would be 1 plus 1/3. My third partial sum would be 1 plus 1/3 plus 1/9. Right. So the question is, how do these partial sums behave? So just a note, be careful, the difference between the harmonic series and the geometric series. Okay, in the harmonic series, the numerical value in the denominator is what's changing. In a geometric series, what's changing is the power. So this would be, harmonic series would be 1 plus 1/2 plus 1/3 plus 1/4. Where here, this would be, 1 would have r plus r squared plus r cubed plus, so notice it's the power that's changing. The base is staying the same. So just make sure you distinguish between the two. All right, how do geometric series behave? Geometric series. Well, the geometric series, a to the power times r to the power n minus 1, we'll talk about this in a minute, converges only if the ratio is less than 1, and it diverges otherwise. So let's take a proof of that. Let's take a look at how this behaves. Why does this happen? All right, let's look at n equals 1 to infinity. A to the r to the n minus 1 is equal to, well, this is, if n is 1, we start with a. If n is 2, we have ar. If n is 3, we have a times r squared plus a times r cubed plus AR to the 4th, and that's all I'm going to write because I'm running out of room. So let's see how we can do this. And hold on one second. All right, so the nth partial sum would add up to the nth term. So that would be the first term, second term. This would be the third term, the fourth term. Whoops. And then we would go all the way up to the n term, which would actually be, if we put n in here, it would be r to the n minus 1. So now algebraically, here's the little trick. We're going to take this nth partial sum and we're going to multiply it by r. So we get r times a times r plus, that would be a times r, ar squared plus ar cubed plus ar to the 4th plus, and then my last term is going to be ar to the n. Right, so here's the trick algebraically. We're going to take this sum and we're going to subtract this sum. Here go my cats again. So if I take this sum and I subtract this sum, these terms, hey, girls, be nice. These terms are going to cancel out. These, oh no, I lost one. Squared, cubed, so forth and so on. Sorry. This is going to cancel. These are going to cancel. And everything is going to cancel. This will cancel with this term. So the only thing that are going to be left are going to be the first term from here and the last term from there. Wait, there is a madness behind this. So now I'm going to, can you see that? Yep. I'm going to factor out the Sn, 1 minus r, a times 1 minus r to the n. Then I'm going to solve for the nth partial sum, a 1 minus r to the nth, all over 1 minus r. All right, so given a geometric series, the nth partial sum can be found by this little algebraic trick. I just wrote it out. I found the nth partial sum, multiply the nth partial sum by r, subtract the nth partial sum, subtracted r times the nth partial sum from the nth partial sum, and we get this little template for the nth partial sum. I know that's a mouthful. All right, but what we're focusing on here right now is that we want to know what is the limit as n goes to infinity of this nth partial sum. Right. Well, this a is undisturbed by the limit because there's no n involved here, there's no n involved here, so this is the only term that's going to distinguish the value of this limit. Well, r to the nth power goes to 0 only if r is between 1 and -1.